Have you ever looked up at a dark cloud and wondered what is actually going on up there right before it starts to rain? It's not just some random thing that happens. Nope, there's a specific, really fascinating process at play. And today, we're going to pull back the curtain and break down the mechanics of precipitation, step by step.
Whether you're trying to figure out a complex weather forecast or you're just curious about a passing shower, it really all boils down to one simple, universal question.
That's it. Why does it rain? It sounds almost childishly simple, right? But the answer to that question is the key that unlocks the entire engine of our weather. So let's build that answer together, piece by piece.
All right, so the first piece of our puzzle isn't actually up in the clouds. It's right here, in the very air that we're breathing right now. It has a hidden ingredient that makes everything else possible.
Yeah, believe it or not, whether you are in the driest desert you can imagine or the most humid rainforest, the air around you is full of water. It's just in a gas form called water vapor, and most of the time, you can't see it at all.
Okay, and here is the crucial point, the thing you have to get. Not all air is created equal when it comes to holding onto that water. Just think of warm air as a big thirsty sponge. It can soak up a ton of moisture. Cold air, on the other hand, is like a much smaller, less absorbent sponge. It just can't hold as much. And that one simple difference, it is the key to absolutely everything.
So, let's just picture a chunk of warm air that has soaked up as much water vapor as it can possibly hold. Meteorologists call this saturated, but for us, let's just think of it as a completely full sponge. It can't hold another drop.
So what happens if you take that full, warm sponge and you cool it down? Well, cooling the air is the atmosphere's way of squeezing the sponge. And because that now colder air just can't hold as much moisture anymore, that extra water vapor gets squeezed out. It has to go somewhere. So it condenses from an invisible gas into tiny, visible liquid water droplets.
So, this all brings us to a really simple three-step recipe for rain. I mean, if you have these three conditions, precipitation is almost a sure thing.
Okay, first, step one, you need the main ingredient, right? Plenty of moisture in the air. Second, you need a trigger. You have to cool that air down to its saturation point. That's our full sponge moment. And finally, number three, you need growth. Those little tiny droplets that just condensed have to start bumping into each other, combining and growing bigger and bigger, until they're heavy enough for gravity to finally win.
All right, so we know we have to cool the air, but how does the atmosphere actually do that on a massive scale? I mean, it doesn't just stick a giant air mass in the refrigerator, right? No, it uses something else, something that acts kind of like an elevator. This right here, this is the engine behind it all. By far, the most effective, most important way the atmosphere cools down huge amounts of air is simply by making it rise. This upward movement is the primary trigger for pretty much all the precipitation we ever experience.
And this process has a name, a word you're going to hear all the time in weather: uplift. It's simple, it's exactly what it sounds like: air getting lifted up into the atmosphere.
Now, this might seem a little backwards, doesn't it? I mean, you're going up, you're getting closer to the sun, so shouldn't things get warmer? Well, the physics of our atmosphere works in a really interesting way. Let's break down exactly why going up means cooling down.
So let's just follow a single little pocket of air on its journey. It starts to rise. Maybe it's being pushed up the side of a mountain, or maybe it's just warmer than the air around it, so it starts to float up, kind of like a hot air balloon. Now, as that pocket of air gets higher and higher, the pressure around it drops. There's just less atmosphere weighing down on it. With less pressure boxing it in, that little air parcel naturally starts to expand.
And here is the real magic trick. That process of expansion, it takes energy. The air molecules have to work to push outward, and that work uses up heat from within the parcel itself. So as it expands, it cools down. It's the exact same reason a can of compressed air gets freezing cold when you spray it. This is a fundamental law of physics, and it's basically the atmosphere's own built-in air conditioner.
All right, so we've looked at all the individual pieces. Now, let's put them all together and see the full continuous cycle in action.
So let's trace the journey one last time. Moist air gets lifted upwards. That's our uplift. As it rises, the pressure drops, it expands, and it cools. That cooling squeezes the sponge, forcing the invisible water vapor to condense into visible cloud droplets. Those droplets then bump into each other, they merge, they grow larger and heavier, until finally they fall back to Earth as precipitation. It's a simple but an incredibly powerful cycle. But here's where it gets really cool. It turns out that the way the air gets lifted, the type of elevator it takes, so to speak, has a huge impact on the weather we actually see and feel on the ground.
And that leads us to the big question. What kind of elevator creates a powerful, booming thunderstorm versus the kind that gives us a gentle, gray, all-day drizzle? Well, the answer lies in the type of uplift, and that's a story for our next explainer.